Hello everyone. The title of our paper is on the quantum complexity of QSETH pair and related problems. It's a joint work with Scott Harrison, Ruizhe, Han Xuanlin, and Chunhao Wang at UT Austin. Today, what I'll tell you is how to use the idea of fine-grained complexity in the quantum world. I'll study the QSETH pair problem and the orthogonal vector problem, and I'll also show you some positive and negative results about their quantum time complexity. So what is fine-grained complexity? I guess maybe most of you are more familiar with NP completeness, which cares about whether a problem is solvable in polynomial or superpolynomial time. Fine-grained complexity, however, cares about what is the exact exponent, like n versus n to the 100. Although both of them are polynomial, it makes a huge difference if you actually run the algorithm in practice. On the other hand, both theory shares a lot of things. For example, like NP completeness, assume P not equal to NP. For fine-grained complexity, one of the assumptions is strong exponential time hypothesis, which basically conjectures that for QSETH problem, when K is large, the brute force algorithm is nearly optimal. Also, like CARP and Cook reduction for NP completeness, fine-grained complexity use the fine-grained reduction to study the relation between different problems. Here is a simple picture about the fine-grained reduction. Suppose we want to reduce problem P to problem Q. Then we start with an instance of problem P. The first step is instance preparation. We'll construct k instances of problem Q of size n1 to the nk. Then we run the algorithm for problem Q to solve these instances, and from these answers, we can compute the answers of problem P. Now, if we have this reduction, and the reduction time is less than the lower bound of problem P, then we'll get a lower bound for problem Q. The main contribution of our paper is first introduce the quantum fine-grained complexity and quantum fine-grained reduction, and also quantum strong exponential time hypothesis. Then we use a framework to show that for a QSETH pair problem in polylogarithmic dimension, Google search is nearly optimal. Also, we show a n to the 2/3 time quantum algorithm for a QSETH pair problem in constant dimension. Notice that for an n to the 2/3 query algorithm, it can be easily obtained from unbalanced quantum random walk algorithm. However, to get an n to the 2/3 time quantum algorithm, we need some data structures which has a uniqueness property, and it doesn't matter in the classical settings. I'll explain it later. Let's first consider how fast can we solve QSETH in quantum. For any k, we can use Google search to get a 2 to the n over 2 time quantum algorithm. For k equals to 3, Porter et al. In 2005 gives a 1.308 to the n quantum algorithm. Unfortunately, for large k, we still don't know any quantum algorithm that runs faster than Google search. So it's reasonable to assume that Google search is the optimal quantum algorithm for QSETH when k is large. That is basically what we conjectured in our quantum strong exponential time hypothesis, or QSETH. Now, the question is, can we directly use QSETH and fine-grained reductions to get some interesting quantum lower bounds? However, the answer is no, because the classical reductions are no longer fine-grained in quantum world. To illustrate this point, let's see an example, the orthogonal vector problem, which is giving you two sets A and B, each has size n of a Boolean vector of dimension d. You need to decide if there exist two vectors in each A in the first set and B in the second set, such that their inner product equals to 0. In 2005, Ron Williams showed that assume strong exponential time hypothesis, a orthogonal vector problem requires nearly quadratic time to solve when the dimension is logarithmic. In quantum, we can use Google search to get an nearly linear time algorithm. Can we show that based on QSETH, the Google search is nearly optimal? To answer this question, let's first take a look at the Van-Williams reduction. We start from a synapse set formula phi, and the first step is instance preparation. We construct an instance of a orthogonal vector problem of size 2 to the n over 2, where n is the number of variables in the CM formula phi. Then we use the algorithm for orthogonal vector problem to solve these instances such that phi is satisfiable if and only if the instance I is a yes instance. Now we can see that the reduction time is less than the CNF set lower bound based on strong exponential time hypothesis. Then we can claim that under SETH, the lower bound of a orthogonal vector problem is n to the 2 minus little 1. We can directly translate it to a quantum version. Notice that in this case, the first step, instance preparation, is unchanged. The only thing we make from classical to quantum is that we can only assume the running time of a orthogonal vector problem is n to the 1 minus epsilon instead of n to the 2 minus epsilon. In this case, the reduction time is already greater than the CF set lower bound and the Q set, just because we can use the Google search to get a speed up for CF set. So it doesn't violate Q sets. Therefore, under Q sets, we cannot get a non-trivial lower bound for orthogonal vector problem just based on the classical reductions. It is because we usually have no time to write all the input data in the instance preparation step. Fortunately, one of the quantum advantage is the quantum query model. For the instance preparation, we can consider the input data as a function. Instead of writing the whole truth table of the function like the classical reduction, we can just implement an input oracle for this function. And when the algorithm needs some data, the input oracle can just compute this data on the fly. Therefore, if the algorithm can solve this problem without accessing all of the data, we can save a lot of time. In quantum, many quantum algorithms can query in superposition to save the number of queries. Based on this intuition, we define quantum fine-grained reduction. From problem P to problem Q, we start with an instance of problem P, with an input oracle O of P. The first step is oracle preparation. We still construct k instances of problem Q like the classical reduction does. However, in this time, we don't actually write down all of the input data of these k instances. Instead, we implement k oracles that can simulate the input oracle of these k instances. When the quantum algorithm tries to solve the k instances, it may query some input data. For each query, our oracle can just simulate the input oracle and compute the answer on the fly in time say of say ni for the ith instance. Finally, from the k solution states, some post-processing step may be required, like Google search, to compute the answer of problem P. Now, if we have such reduction and the problem P has no sum of CNI times QNI quantum algorithm, then we can claim that Q has no QN time quantum algorithm. That is to say, if the reduction time is less than the quantum lower bound of problem P, then we'll get a quantum lower bound of problem Q. So can we use the quantum fine-grained reduction to get a lower bound for a orthogonal vector problem? We know that the bottleneck of the classical fine-grained reduction is the instant fabrication step, which is as follows. We divide the variables of the CF formula into two sets, XA and XB, and then we consider all possible half assignments to these variables. For each half assignment, we construct a vector indicates which clauses are satisfied by this assignment. Notice that the vector construction is very local. That is to say, for each single vector, it can be computed in a very efficient way, and it has a very succinct representations. Therefore, we can just implement an input oracle for a orthogonal vector problem. For each query index E and I, it returns the Boolean vector corresponding to this index. The query cost is just polynomial in n. And so, if the orthogonal vector problem has n to the 1 minus epsilon quantum algorithm, then the CF set has poly n times 2 to the big N times 1 half minus epsilon over 2 quantum algorithm, which is faster than Google search and is impossible under QSETH. From this example, the take-home message is that if a reduction is local, that is to say, it has very succinct representations in the input construction step, then it could be made as a quantum fine-grained reduction. Here is a summary of the results in this work. We studied the closest pair problem, orthogonal vector problem, and bichromatic closest pair problem in constant dimension and polylogarithmic dimension. We already shown the quantum lower bound for orthogonal vector problem in polylogarithmic dimension. In the remainder of the talk, I'll concentrate on the closest pair problem. Here is the definition of the closest pair problem. Given a set of n points in a d-dimensional space, you need to find a pair of distinct points A and B such that their distance is the smallest among all pairs. Classically, the famous textbook algorithm is the n log n time algorithm by divide and conquer. In 1995, Kuller and Matthias gave a 2 to the d times n randomized algorithm. On the negative side, Yao proved that the lower bound is omega n log n. Further, Karthik and Manuganksi in 2019 improved this result to n to the 2 minus little 1 and the strong exponential time hypothesis for polylogarithmic dimension. Let's first consider the quantum lower bound for a closest pair problem. In constant dimension, we can easily get an omega n to the 2/3 lower bound just from element distinct lower bound by Erickson and Xu. The hard part is the polylogarithmic dimension. We can show that under QSETH, the lower bound is n to the 1 minus little 1. The reduction is as follows. We start from CF set problem and reduce it to a orthogonal vector problem, which we already shown, and then we reduce the orthogonal vector problem to bichromatic closest pair problem, which is giving you two sets of points. You need to find the closest pair between these two sets. And finally, we reduce the bichromatic closest pair problem to closest pair problem. For the second step, it easily follows from Graham-Williams' paper. For the third step, we adapt the proof in KM19. One thing we need to care is that in their reduction, we will construct many closest pair instances, and we do not have enough time to solve all of them. Instead, we construct a superposition of the instances and use Google search to find the minimum answer among the instances. By this reduction, we can prove that assume QSETH, the closest pair problem in polylogarithm dimension, cannot be solved by any quantum algorithm in time n to the 1 minus epsilon for any constant epsilon. Now, let's consider the quantum upper bound for closest pair problem. In polylogarithm dimension, we already proved that Google search is nearly optimal. In constant dimension, however, the quantum upper bound is not very easy. We consider the decision version, that is to decide if there is a pair with distance less than epsilon. The n to the 2/3 query quantum algorithm can be easily obtained from unbalanced element distinctness problem. We consider a random walk over all possible subsets of size n to the 2/3. In each step, we first check whether the current subset contains the epsilon closest pair. Then we randomly remove one vertex from the subset and we randomly add another vertex to the subset. Then we get a new subset. We can see that the underlying graph is a Johnson graph. So the quantum query complexity is the n to the 2/3 by this formula. To transform an n to the 2/3 query algorithm to n to the 2/3 time algorithm. However, two factors are very important, U and C, where U is the cost for taking one step in the random walk, and C is the cost for checking if the current subset contains the epsilon closest pair. Now, the question is, can we maintain a dynamic set of points that supports three operations: add a point, delete a point, and query the epsilon closest pair? Classically, we have some point location data structure like Voronoi diagram or fair split tree to solve this problem. In quantum, however, the data structure must be history independent. That is to say, for the same data, regardless of the operation orders, the data structure must have the same memory layout for this input data. It is because we store the data structure into the quantum state. If we get the same subset from different paths in the random walk, and the data structure is different, then the quantum interference will be destroyed and the algorithm will collapse. In our paper, we use the registry and hash table and skip list to achieve such a data structure for a set of points. Moreover, for our data structure, the update time is just polylogarithmic in n, and the checking time is constant. So the total quantum time complexity is about n to the 2/3. Next summary here. In this talk, we introduce the quantum fine-grained complexity, quantum fine-grained reduction, and the QSETH, and we also proved the quantum lower bound for orthogonal vector problem and the closest pair problem. We also show some quantum upper bound for these problems that nearly match our quantum lower bounds. Here are some open problems. The first is, can we find other applications of our sublinear time reductions? Notice that our quantum fine-grained reduction can be achieved in sublinear time based on oracle constructions. Can we use the similar idea to prove other fine-grained lower bounds for like classical streaming algorithms or classical sublinear algorithms like sketching? The other open problem is, can we show quantum fine-grained complexity for other problems? Notice that Berman et al. Showed an omega n to the 1.5 lower bound for edit distance based on a different version of QSETH. Can we prove similar results based on our version of QSETH. Also, can we show quantum fine-grained complexity for coding problem or lattice problem, like the quantum fine-grained lower bound for CVP or SVP? Thank you.